Hello and welcome back. We are discussing section 2.2, Techniques of Differentiation. We're on to our third and final learning objective, study rectilinear motion and the motion of a projectile. We will primarily be doing the latter there, motion of a projectile. So here's our example. Diver's height in meters above the surface of a pool, t seconds after jumping is given by this thing. So you can sort of imagine that there's going to be a period where they're headed upwards a little bit and then headed down toward the water. So the questions we're supposed to answer are how quickly is the diver rising or falling after 0.2 seconds, after 1 second. So I want to make mention of some key phrases here. As usual, since this is happening in a particular section, your brain sort of automatically understands that the new tools we've introduced in that section are going to be the most valuable. But because we're going to be taking exams that will cover a variety of material, I just want to talk about some of the phrasing here that we can use in general to determine what sort of strategies are appropriate. So how quickly is a very common phrase to indicate the derivative. So when we ask how quickly, that's about a speed, a rate of change. So if we're asking how quickly height is changing, that's going to pertain to f prime, because the derivative is the rate of change in some function. So this rising or falling bit is just going to be whether h prime is positive or negative. Now we know that our inputs are in seconds, so 0.2 seconds must be an actual time value we're supposed to plug in, similarly for 1 second. But our first task is going to be figuring this out. What is the derivative function for h? So we could use, in theory, we could go back to 2.1 and use the limit as h goes to 0 of this slope fraction, but I think it's a lot easier to use these shortcut rules we've developed. So h prime is comprised of the derivative of this whole expression. This is what we were given. Again, notice that we've changed the input variable to t because t is our input in this case rather than, say, x. Okay, and then we'll make use of all of our clever rules here. We've got a bunch of constants, 4.5 and 10. Those can all get pulled out. You could even pull out the 10, although I'm not convinced it's all that useful because we can figure out the derivative of 10 without too much trouble. And then the pieces that are left are just the components that have variables on them. And these are relatively nice because they look exactly like power rule is ready to handle them. With the possible exception of this, t is really t to the first power, so that's not too much of a stretch, but there's our extra expression. Okay, so really, all the derivative stuff has been reduced to what is the derivative of t squared, and what is the derivative of t. So these are both power rule computations we can do pretty quickly. So the 2 comes down, so we get a multiple of 2 out in front, and then it's t to the first power, since that exponent gets decreased by 1. And then for our other expression, okay, so here is 2t, the derivative of t squared. And then the derivative of t, the 1 comes down, so we have 1. But then if we take away 1 from the exponent, we get t to the 0th power. T to the 0th power is 1, so we'd have just a factor of 1. Notice that all the ddt things are gone. And we forgot about not the most important, but actually the most satisfying perhaps, since it makes stuff go away. Derivative of a constant by itself is just 0. So derivative of this line with the no slope is 0. And all that's left here is our actual derivative expression. All the ddt's are gone because we accomplished all these little mini derivatives we were being asked to compute. So we could tidy that up a little bit to h prime equals negative 9.8t plus 4.5. And then just a reminder about that derivative operator. So the ddt thing doesn't go away until we actually compute the derivative. So once we figure out that the rate of change of t squared is 2t, then the derivative, the ddt thing, goes away. Okay, so now we need to plug some stuff in. We've got our derivative function. We've got 2 things to dump into this. So either t equals 0.2 or t equals 1. We'll do both those computations. So this just asks us to go to our derivative function and replace t with 0.2. With a little simplification, we get 2.54. And then h prime of 1, same deal, go back to the derivative function but plug in 1 for t. And that gives us a negative 5.3. Okay, so the interpretation piece, as usual, is one of the most important facets. So that h prime of 2 means that after 2 seconds, the diver is rising. Remember, this is not just an actual height. It's not saying that the diver is 2.54 meters off the ground. The rate of change, this derivative thing, is telling us how is this height changing as time goes on. So rising is an indicator of rate of change. So it's rising at a rate of 2.54, and then units on output are meters, units on input are seconds. So the units on the derivative are meters per second. Same deal for 1 second. However, because the diver has a negative rate of change, that implies that he or she is falling at that point. So negative 5.3 means falling at a rate of 5.3 meters per second. Same units because it's the same derivative. That's our final learning objective accomplished for section 2.2. I'll see you for the next section.